Right. So good. Thanks for reminding me that we have, yeah. All right. I guess I'll move me over a little bit. Yeah, I guess that works. Um, and so here's the claim. Um, and it's actually, we can read it from the text as well, which I think I have here, which I suppose I should move down. I'm not sure. Oh, um, um, right. So what is it? What is the statement of the theorem here? Let me change my view so I can see more betterly what we're looking at. And I guess I have to go over here. So is this the median of a trapezoid is parallel to its bases, and its length is equal to 1/2 the sum of their lengths. Okay, then principle 5, we'll read these together. The length of the median to the hypotenuse of a right triangle. Okay, 1/2. Okay. So let me write that down. Let's see if we can prove that. Principle 4 of trapezoids. Oh, and let me put the. Guess I just turned that one off. Okay, so principle 4 of trapezoids is going to state that got a bit of a glare, huh? And then it's dark. Can't win with this thing. All right, and it won't stay in place either. Too many knobs to tighten. All right, I'm just going to say that has to be good enough. So principle 4 of trapezoids, the median of a trapezoid is parallel to the bases and is 1/2 the sum of their lengths. Okay, so we need to make a proper diagram for this. By the way, I have now in my arsenal, I went to my office to recover these things, which required special dispensation from the dean. But this is a better compass. This is also a very nice compass. This is from my collection of compasses. Here's a larger one of the same sort of style. And then I have this one. But of all these, I kind of like the one on the left. It's sort of the simplest. It's made by Dürer, which is named after the famous perspective artist, Dürer, D-U-R-E-R. Anyway, so when we get to circles, we'll have that available. For now, all we need are straight edges. Right, so we want, so how do you find the midpoint? Well, actually, so I'm going to draw a trapezoid like so. I guess I don't want to make it that far over though, because then we'll have a problem with our diagram. So maybe something like this. Is that, it looks like it's almost isosceles, huh? I didn't mean to make it isosceles, but never mind. Don't assume that it's isosceles, right? This is a general trapezoid where BC is parallel to AD. And I'm going to find the midpoint here. Now, one way to find the midpoint is to use compass. And let me just quickly demonstrate that. What you do is you put the point of your compass here, and you draw a little arc here, and another little arc here. And then you put the compass on the other side. Oh, that didn't quite. Yeah. So then you see those arcs. So you draw the line segment connecting where those arcs intersect, and I'm going to say it's right about there. And that will be a perpendicular bisector, but it'll be a bisector. Okay, so there's that bisector. Okay, you want to do the same thing over here? Yes, you do. Of course you do. And so I make a bit of an arc here, make another little bit of an arc here. And we'll repeat this when we do circles, but oh yeah, almost missed that one again. Right, so those, you can't really see the arcs up there, huh? All right, see, those are barely intersecting there, and so when I connect those points of intersection, I could draw the perpendicular bisector, but I'm really just interested in the midpoint, which is going to be right about there. So that means that this length is the same as that length, and this length is the same as that length, right? Maybe if this thing were over here, shining the other way, of course, then it's going to be in the way. I've yet to figure out my arrangement here, but yeah, that seems a little better. So now, so I'm going to call this M and call this N. And I'm going to extend AD. What allows us to do that? I think it's like axiom 2, right? It says any line can be extended indefinitely. And then I'm going to draw this segment here. Does that look convincing? Okay, so I'm going to draw the line segment through B and through N and intersecting the extended line there. Let's call that X, marks the spot. Okay, does anybody see what I'm going to do next? I have been writing this down, have I? I could make like a little narrative. How about that? Have a narrative proof instead of the more long-winded. So, so how about what would the narration look like? So here's my proof. It doesn't have to be in 2 columns all the time, right? So I can say let A, B, C, D be a trapezoid with, let's see, AD parallel to, oh, kind of ran into my X here, didn't I? BC. All right. And let M be the midpoint. And again, we know these things exist axiomatically, right? The midpoint of DC. Okay, that's just as I've drawn in the picture. Then draw BN, so like the ray, to meet AD, the ray, right, at X. Okay, so now I know that since CN is congruent to DN, right? That's the definition of midpoint. And what else do we know? Right. Okay. It's going to be essentially angle side, I guess. Right. And so do you see what the two angles are? Well, let me indicate them in the diagram. So this angle is congruent to that angle. Why? C and B is congruent to angle DNX. These are vertical angles, right? Furthermore, angle, and this angle here is congruent to that angle there, and what justifies those? Angle CBN is congruent to angle CBN DXN, right? And these are alternate interior angles for, to be thorough here, DX cutting BC parallel to AD. Right, so if you have a transversal cutting parallels, alternate interior angles are congruent. That was my parenthetical justification there. And so now we have triangle CBN is congruent to triangle DXN, where in fact C is congruent to D. We didn't establish that, but we get that because they're corresponding parts. But I'm just saying that C and D correspond, X and B correspond, and C and D correspond as angles, right? Is this reasonably visible here? Okay. And so corresponding parts are congruent. In particular, Bn is now congruent to Nx. So therefore, Bn is congruent to, what are we trying to show again? Oh, right. I don't know if I'm there yet. Anyway, Bn is congruent to, what else do we know? Bn is congruent to Nx. Shall I mark that? It's like three hash marks now, right? Is that good for anything? I haven't even drawn the median in yet, have I? This is the median. We want to show that that's parallel to the two bases. So Mn is, we want to show that Mn, and one way to do that is to get corresponding angles. I suppose I could do the same thing on the other side, but I don't know what good that would do me. So I now know that, oh, okay, this is good, right? This angle here, which I'll mark with a little circle, is congruent to this angle here. I think that's going to be sort of, well, we know that those are alternate interior angles when parallels are cut by a transversal. So that's not a new thing, is it? Right. Oh, and we didn't justify, this is by angle side angle now, right? So what good does that do me? Okay, right. So n is the midpoint of bx. That may or may not be useful, but would that be useful? Okay, so angle BCN and NDX. BCN and NDX. Yeah, those are congruent. So BC and DX are congruent. BC and DX, that's true. Right. Okay, so we're going to use, do you recall the theorem that the median line for a triangle, I don't know, did we prove this? The median line for a triangle is half the base. I think we did prove this, right? So that, so now we've established that MN is half of AX. So MN equals half of AX because the median of a triangle is half the base. And AX, we can substitute for AX the sum of its parts, which is AD plus DX, and we can substitute for DX BC, right? We showed that DX is congruent to BC, their corresponding parts, right? Did I write that out? No. So let's write it here. And this is because corresponding parts of congruent triangles are congruent, right? So that BC is also congruent to, I'm kind of all over the place here, sorry, DX. Oh, and I'm not even on the visible part of the screen, okay. So what I do over here, I said MN is half of AX because, and I didn't write out the justification, kind of short on space here. That's because the median line for a triangle, I think we proved that, didn't we? The median line of a triangle is half the base. If not, we can do that. Maybe we have to go back and do that. And is parallel to the base, right? Oh, is that true? So in triangle ABX, M is the midpoint of leg AB, right? And N is the midpoint of side BX. So since M is the midpoint of AB, by a premise of this theorem, N is the midpoint of BX, as was just proven. Segment MN is a mid-segment triangle of triangle ABX, and therefore is parallel to the base and equal to its half. Right. So did we prove that? So maybe we should go back and make sure. How would you go ahead and prove that? So the claim is that what? What's it called? The midline? Mid-segment? A mid-segment, I'm going to call it, of a triangle is parallel, I'm pretty sure we proved this, but just to be sure, to the base and half its length. All right, let me draw a diagram to illustrate that. So it's going to look something like this, right? So I'm going to draw this to be 2 centimeters, so I can easily, oh, that's actually 3 centimeters, isn't it? Draw the midpoint there. And then this is, trying to draw a fixed length here so I can, okay. So it goes from 8 to 15, so that's 7. So I know it's cheating to actually measure, right? So there's the midline, the mid segment for this triangle, meaning that these are the same and these are the same. So if this is A, B, C, and this is M and N. So we're given that M is the midpoint of AB, and N is the midpoint of CB. And we want to prove that MN is parallel to AC, and further that MN is half the length of AC. Yeah. Again, I kind of want to draw the parallelogram. So the let's see if we can get this. Yeah, so this is one where I think you want to extend. So here's my proof. Draw, what do you want to call it? CF parallel to AB and meeting MN, the extension of MN at, should we call it E? Okay, so I want to draw this parallel to that. I'm just going to kind of fake it, okay? Does that seem like it's parallel? Okay, and here's the extension of MN. And so that's going to meet at F there, right? How are we doing? Is that good? Is it visible? I'm not following the chat like a bad person. Chat. Is there anything going on? Oh, there is. I'm here. You didn't call me. Really? I'm pretty sure you're here. This is a private message, so, but I may have just skipped over your name inadvertently. Yes, you are. Okay, I'm marked in, and Tia is here. Okay, great. All right, so so now what have we got? Well, the plan is to prove that these two triangles are congruent. Do we have enough to do that? Yeah, I know that these are vertical angles. And I know that these are alternate interior angles. So I know that, so should we so we did this construction, right? That's allowed axiomatically. So I'm going to say statement and justification. We'll do the 2 columns here. And maybe make some nice guiding lines to help us. So, so I'm going to say that Bn is congruent to Nc, and that's the definition of midpoint, which is given that that's the midpoint, right? And we know that angle BNM is congruent to angle FNC, and those are vertical angles. Vertical angles are congruent, and we know that angle ABC is congruent to angle BCF, and that's because the transversal BC cuts AB parallel to CF, right? All right. And is that enough? Yeah, I think we got then angle side angle. So triangle MBN is congruent to triangle FNC. Oh, sorry, FCN, right? And that's by angle side angle. So that gives us that MN is congruent to NF, right? Corresponding parts of congruent triangles are congruent, right? And so we also know that, so now we want to say that this is, that MN is parallel to AC. Can we say that? Well, we know corresponding angles are congruent. So I know that this angle here is congruent to that angle there. Yeah, this angle. So let's go ahead and say that. So I know angle BMN is congruent to angle NFC. That's an angle. And that's for the same reason, right? Corresponding part, this is like a ditto, repeat the reason above. Corresponding parts of congruent triangles are congruent, but that means then that I don't know, what does it mean? We want to establish that MN is parallel to AC, right? And so if I could establish that these angles were congruent, that would do it, right? I don't know, is it obvious that this is a parallelogram? Opposite sides are congruent, is that true? Yeah, right, okay. So that does it, right? Because if opposite sides are congruent, that's a sufficient condition for it being a parallelogram. We proved that, right? So how do we know? Well, we have that FC, I don't know if I said this, so let's say it. FC is congruent to BM. And that's, again, corresponding parts of congruent triangles are congruent, right? So this side and that side correspond, right? So they're congruent. And this side is congruent to that side, but that was given, right? So I'm going to say AM is congruent to MBM, and therefore AM is congruent to FC. This was given, and this is the transitive property of equality. Right, if two things equal to the same thing are equal to each other, so FC is equal to BM, AM is equal to BM, AM is equal to FC. Okay, so that means that AMFC is a parallelogram. I should use my abbreviation, huh? And that's because opposite sides are congruent, right? That we proved that earlier. Oh, sorry. So since it's a parallelogram, opposite sides are parallel, right? So MN, that was a little bit tricky. MN is parallel to AC, and N is the midpoint of MF, right? Did we say that? MN is equal to NF up here, right? So that means that that MN is half of AC, which is what we wanted to prove, right? And that's all of it then. All right, boy, that was kind of a pain, huh? All right. So any questions about that before we saunter on? I think that kind of gets the gist of what we wanted from chapter 5 here. I guess I want to get up our textbook on the screen here, which I do like so. Here. Okay. And so we got principle 4. Principle 5, the length of the median to a hypotenuse of a right triangle equals 1/2 the length of the hypotenuse. Yeah. Because why is that? Yeah, some of these you have to think about them a little bit, right? So we know that AM is congruent to MB. If we were to draw the median segment for that triangle through M, we would get half of CB by the theorem we just proved. Yeah. Well, that sounds like a good challenge for you. So the principle 6, the medians of a triangle meet in a point which is 2/3 the distance from any vertex to the midpoint of the opposite side. 2/3. Now we're talking. And so how do you prove that? So yeah, we basically maybe we want to prove both of these, but let's do that as part of the review, because I do want to get on to circles today and we're short on time. So note, we will prove in our copious free time So it remains to prove principles 5 and 6 for medians and midpoints. And let me just say that then in the in our box. So I'm going to say, oh, I need to publish this still. Okay, week 4, there it is now. As a discussion, we would like a new topic, which is going to be proofs of theorems, principles. I guess they are theorems, but principles, because they're referred to as principles in the text, 5 and 6 for midpoints. So I'm going to add that and publish it and then edit it. So can I copy stuff out of here? I can't. I would think that I could, but apparently it's not that kind of a thing. Okay, so that's no problem. It says the length of the median to the hypotenuse of a right triangle is 1/2 the length of the hypotenuse. So let's edit this and we'll say principle 5. The length of the median to the hypotenuse. Hypotenuse is the side opposite the right triangle, right? The right angle of a right triangle is 1/2 the length of the hypotenuse, and principle 6 says the 3 medians of any triangle intersect at a point which is 2/3 of the way from the vertex to the midpoint for any median. I think I pretty much said the same thing. Okay, so I'm going to post that up there, save it, and we'll have it for discussion later. We do want to get onto circles, and so that's one way of sort of pressing ahead, as it were. Okay, so then I want to go back to our text, and we see principle 6. Oh, that was principle 6. Okay, right. And so here are some solved problems. You like this one? Proving a midpoint problem. So given a quadrilateral ABCD, see it there? E, F, G, and H are midpoints of the 4 sides, respectively. And to prove, when they say respectively, is it clear what they mean? Like E is the midpoint of AD, F is the midpoint of AB, and so on. So, yeah, in respect to position in the statement. We would like to prove that the quadrilateral EFGH is a parallelogram. And the plan is to prove that EF and GH are congruent and parallel. Well, based on what we just did, we know that EF is 1/2 of dB and GH is also 1/2 of dB. So they're equal, right, by the transitive property of equality. And we know that EF is parallel to BD and GH is parallel to BD. And so by the transitive property of parallelism, EF is parallel to GH. Right? And so we also have a theorem that says if two sides of a quadrilateral are congruent and parallel, then the quadrilateral is a parallelogram. And then you have your supplementary problems, and those are all worth looking at too. So now let's open up the circles chapter. So I'm going to say open, and I think that's chapter 6, circles. The circle and circle relations. All right, and this is sort of crucial because all of trigonometry is about circles and triangles, and sort of this wraps it up. The following terms are associated with a circle. A circle is a set of all points equidistant from a fixed point called the center. The circumference of a circle is the distance around the circle. It contains 360 degrees. So the degree measure of the circumference is 360 degrees. The radius of a circle is a line segment from the center to a point on the circle. We know all these, right? Central angle is formed by 2 radii. Arc is a continuous part of a circle. And the symbol for arc is this little curved line like so. A semicircle is an arc measuring half of the circumference. So the degree measure of a semicircle is 180 degrees, right? A minor arc is an arc that is less than a semicircle. A major arc is an arc that is greater than a semicircle. So when you refer to the arc BC, you're usually referring to the minor arc, the one that's half, but there's also one that, less than half a semicircle. Sorry, less than half a circle. Okay, so then we have these things, right? A chord connects any 2 points on the circle. A diameter is a chord through the center. The secant is an extended chord, and a tangent just barely glances off the circle, right? Am I monitoring the chat? I lost the chat. There it is. Okay. Yeah, all right. So here's an inscribed polygon, yeah, with its circumscribed circle. So an inscribed polygon is a polygon all of whose sides are chords of the circle. And the circumscribed circle is a circle passing through each vertex of the polygon. Now, every triangle has a circumscribing circle, right? But not every quadrilateral does. It's pretty easy to imagine a quadrilateral that does not have a circle containing all 4 vertices, right? Just imagine moving C off the circumference. It's still A, B, C, D is still a quadrilateral, but there's a unique circle containing A, B, and C. A, B, and D, and if it doesn't pass through C, then it's not circumscribing for that quadrilateral. Okay, a circumscribing polygon is a polygon all of whose arcs are tangent to the circle. So this is the other direction, right? Concentric circles are circles that have the same center. Okay, let's get into our principles. The diameter of a circle divides it into 2 equal parts. That's sort of, yeah, obvious, right? If a circle divides a circle into equal parts, then it is a diameter, the converse of principle 1. Principle 3, a point is outside on or inside a circle according to whether its distance from the center is greater than, equal to, or smaller than the radius. Again, seems fairly self-evident. Radii of the same congruent circles are congruent, same or congruent circles. Diameters of same or congruent circles are congruent. In the same or congruent circles, congruent angles have congruent arcs. Okay, that's a little bit more involved, but it still seems quite reasonable. In the same or congruent circles, congruent arcs have congruent central angles. Okay, so congruent arcs in congruent circles subtend central angles that are congruent. So that word subtend is one that I use advisedly here. Principle 8, In the same or congruent circles, congruent chords have congruent arcs. Yeah. So if the chords are equal in a congruent circle, then so are the arcs. If it's not a congruent circle, then all bets are off there, right? Principle 9, in the same or congruent circles, congruent arcs have congruent chords. So that's sort of the converse of 8, right? So 10, a diameter perpendicular to a chord bisects the chord and its arcs. All right, now we're getting to one that maybe deserves a proof, right? A proof of this principle is given in chapter 16. Oh. We could find it there. I think we can prove that without looking at it, right? Let me see. So here's the statement of principle 10. And let's get it on the DocuCam. All right. You know, I have this. Does this work? I have a new surface here, which apparently, no, I need to have this thing open. Yeah, which I could maybe try to write here. So, so the claim is that now I've forgotten it. Principle 10, right? Who remembers principle 10? Oops. A diameter perpendicular to chord bisects the chord and its arcs. Okay. Let's see if I can write like, no, that's bad. A diameter perpendicular. Yeah, see, I can't write with this thing, or I'm going to have to learn. Perpendicular to a chord has or bisects the chord. And its arcs. This is terrible. Yeah. All right. So there. All right. We'll go back to the DocuCam. It was worth a try, right? Okay, so we have here we go. So circle principle 10. A diameter perpendicular to a chord bisects the chord and its arcs. Okay, do we need to draw a picture of this? And I can make my circle here now. Right? I've got a fancy circle maker. Make it a little bit bigger. All right. And oh, you can't see that. Is that better? Okay. So here's the center, right? So if I have a chord, let's say like AB here. And I have a diameter that passes through the center. If that diameter is perpendicular So this is the center point O. I'm going to call this CD, and maybe call this E. So I've got now 6 points altogether in contention. So what are we given? Chord AB and diameter CD perpendicular to AB, right? We want to prove that AE is congruent to BE. AE is congruent to BE, and AE, the arc, oh, sorry, AD is congruent to BD, the arc BD, right? So they make a little curved thing over the top if it's an arc, right? Okay, so we can draw the radii. So what are we given? So yeah, so should we do the 2-column thing? Statement, justification. All right. And so we're given CD, well, let's just say diameter CD perpendicular to AB. I just said that. Oh, I know. No, so that's given. So we can draw, and do I have to say that we can draw? I mean, it's axiomatic at the very basic level, so I'm not even going to bother saying it, right? We can draw these 2 radii. So we have that OA is congruent to OB. All radii are congruent. And what else? OE is congruent to itself. That's the reflexive property of congruence. And what else? So now we have 2 sides. Do we have an angle? Yeah, we have an angle, right? That OEA is congruent to OEB. All right angles are congruent. So now I've got angle side side. Oh, that's the ambiguous one. But I have hypotenuse leg, right, for a right triangle, right? So that allows me to conclude that triangle OE, and that had to be the plan, right? Once you establish that triangle OAE is congruent to triangle OBE, and here that's hypotenuse leg, which we can just abbreviate that way, then we have the corresponding parts are congruent, namely AE is congruent to BE. Corresponding parts of congruent triangles are congruent. So that's part of what we wanted to show, right? The other thing is that the arcs are congruent. So now if we can show the chords of the arcs are congruent, then we can show the arcs are congruent, right? That was one of the principles. Can we show the chords are congruent? I suppose we can, right? since we now know that this is congruent to that, we can now say this triangle here is congruent to that triangle there. Right. This thing is congruent to itself, and we have a right angle. So I'm just going to cut to the chase on that. Say triangle AED is congruent to triangle BED, and that's because angle side angle. Sorry, side angle side. Right. And I didn't say ED is congruent to itself as a separate statement, but I think it's pretty clear. And you know, those are right angles there, right? So I suppose, yeah. So that means that AD is congruent to BD because corresponding parts of congruent triangles are congruent, and that allows me to say then that arc AD. This was the segment, right? This is the arc. And that's because congruent chords in congruent circles, or in the same circle, that's the universal shortcut for a circle. You make a little circle, are congruent. Then we're done, right? QED. All right, questions about that? Again, I've obscured the chat, so I haven't been looking at that. Xavier has put in a backslash. This is the big new development. Is that an indication that did I count you as here? Yeah, you were marked absent. So that's a way of saying, check, I'm here. All right. Good. I'm glad. How about more principles? Principle 11, a perpendicular bisector of a chord passes through the center of a circle. So it's a diameter, right? How would you prove that? Well, so you know that AP is congruent to BP, right? You could draw the triangles and show that you've got I can't think of a good plan for this. I mean, it seems obvious enough, right? But the obvious is the enemy of the true. So if you were to extend DP, it would have to pass through O. And how could you show that? Well, you could, you know, show that it's twice the radius. I mean, that's one way we identify a diameter, is it's twice the radius. Or you could show that the degree measure of the arc is 180 degrees. So you show that's a semicircle. Yeah. Okay, I'm just going to talk through this one quickly because, you know, otherwise we'll never make any progress. But you know, thinking about it for a little bit, I have a plan. So let me share with you what I'm thinking. So I'm going to draw a little circle. And hope that it's reasonably visible. It's very sharp. It's not reasonably visible. Okay, that's better. So here's the center of the circle, right? Here's a chord. And I'm going to make the chord 5 centimeters. So 2.5 centimeters would be the midpoint. So we're given that, what this is, A, B, I guess. And we draw this guy perpendicular and extend it, right? And when we extend it, it's going to meet the opposite side somewhere, right? So should we call this C, D? And then I'm going to say that since we know that these are equal, if I draw these triangles here, now I see my plan failing. You have to be very careful not to assume things that you don't know for sure, right? So we know that's a right angle. We know that we have one side in common. Oh, we have another side in common, right? Which is ED. So we have side angle side. So triangle ADB, sorry, ADE is congruent to triangle BDE by side angle side. Right, this thing is congruent to itself. They both have a right angle. That's the same. Right, so that says that BD is congruent to AD. That's, corresponding parts of congruent triangles are congruent. So we can conclude that these are the same. I guess similarly, yeah, similarly, triangle, let's try to complete these here. Triangle AEC is congruent to triangle BEC. And so, right, because this thing is congruent to itself, which implies that AC is congruent to BC. Well, that says that arc AC plus arc AD is congruent to arc BC plus arc DB. And the reason for that is equals added to equals are equal. No, that's kind of, that's obvious. Yes, it's the enemy of the true. But that says that AD or CD is equal to, oh, well, let's see, how do we say it's going? CAD, that arc, right, is congruent to the arc, sorry, CBD, right? And so they must be half, right? So the measure of CAD plus CBD is 360, it's the whole way around. So twice CAD is equal to 360. And that says that, this is a lot of trouble. I was trying to be quick. How are we doing time-wise? We're out of time, huh? Okay. So we got a semicircle. How far along are we? Not very far at all is where we are in chapter 6 here. So if we go back to the text, we see.
Is that behind where we're supposed to be?
Yeah. But, you know, we kind of lost a week because of the weirdness of the way the semester started. So we're really only about a week behind, which we'll have to make up for at some point. Okay, so they have some vocabulary. Then they have tangent principles. There's a bunch of those, and we'll take up with the tangent principles tomorrow. Those are sort of important, huh? You can see there's a lot of them too, right? And then what else do we have? Angle measurement principles. And there's a little table of angle measurement principles, some solved problems, and supplementary problems. So proving angle measurement problems stated in words. Okay, so those are solved problems, right? So we'll have tangent principles and angle measurement principles, and then we'll be ready to finish up the geometry section and move on to functions, which is going to be a bit of whiplash, folks. Completely different world, right? We go from geometry to sort of pure geometry almost to almost pure algebra, right? And then we'll start mixing them together. Algebra and geometry is, the mixture of those is pretty much what geometry is, but we're out of time. So that was a good question. Any other questions?
So you just want us to reread chapter 6 again tonight?
Yeah, and there's actually, I can post them up if you want to get started on those exercises. I will make those available for you. Where is that? That's here. I can hang around while we're doing that. So I'm going to say I'm done with this. Am I done with that? I guess I am. I must have saved it or something, right? So if I go back to here, we have geometry 4, but there should now be geometry 5. And so we're going to say, yeah, add an assignment, which is a new assignment. The assignment is going to be geometry 5. Add that item. I guess publish it, edit it. And that means edit it again, strangely. And I don't really need to say anything other than, yeah, there are points. And this is submission type is external tool. And we need to find our external tool, which is mom. Hello, mom. There you are. And which mom is this? This is, geometry 5 and 6. I guess it's sort of a mixture of those, huh? And so we'll place that. And I guess we want to select that. And then we want to say it's due by the end of the week. Okay. And we'll save that. All right, so we'll get into that tomorrow. Sorry for going over, folks. Have a pleasant afternoon, and I will be in my office for the next hour if you want to stop by.
Quick question, Professor.
Which
Do
is
we
the
need
Zoom
to
room. Yes,
cover
go ahead. Sorry.
chapter 6 in order to get started on geometry 5? Yeah, right?
Yeah, you should read through chapter 6 first. Yeah. So, but you've got all week to do that. So we'll finish that up tomorrow and then start in on the review.
Sir.
Yeah.
I had to come in late because Canvas was acting kind of weird and it wasn't showing me the class. So can you just mark me here because I've been here for like the whole thing. I just don't want to get marked late because I wasn't here from the beginning.
Let's see if I can get my mouse over here, but I have to sort of know who am I speaking to so I can do that.
Adrian Aguilar.
Oh, Adrian. Okay, great. Yeah, I see you now. And yeah, thanks for speaking up. All right. can you do figure 612? Yeah, well, as long as, since it's office hours, we'll just hang out here. Figure 612, is that in the homework? I'm not sure which figure 612 you're referring to. 612, is that in the text? Okay, I lost the chat again. I accidentally misspelled some words in the homework assignment when it came to proving some problems. Is there anything that can be done about that? Yeah, so let me make a note, Maria. I can just make sure to go through that and look at it individually. Okay, so remind me tomorrow if I haven't done that, that I need to do that, but I will attend to it soon here, I think. So 612. Oh, I see that. That's this one here. Okay, my thing is stuck over there. So let me, yeah. So 612 is principal 12. In the same or congruent circles, congruent chords are equally distant from the center. Yeah, so the distance from the center is that length of the perpendicular OE, and that must be the same as OF there, huh? Equidistant from the center. So what would the plan be? Yeah, I think if you were to draw the radii AO, BO, CO, and DO, those are all congruent, right? So that would mean that triangle AOB is congruent to triangle COD. COD. And then you could also get, so the perpendicular bisector OE is going to make triangle AOE congruent to triangle BOE, and similarly CFO and DFO are congruent, and since the big triangles are congruent, the little triangles will also be congruent, and so AO is congruent, sorry, EO is congruent to FO, and so they're equidistant. That's just talking it through out loud. Will that do? It was question 9. Oh, in the homework? Okay, let me take a look at that. So not this homework, but the this homework. Oh yeah, that looks like a lot of work, but I think we'll get there. But I think you're probably referring to. And here, I think I need to just. Go back. This one. Question 9. The altitudes to two sides of a triangle are congruent, then the triangle is isosceles.
Anything positive.
Okay, well, let's take up with that first thing. Do you want to do that now? So triangle ABC have congruent altitudes AD and BE. Draw the figure for reference. Yeah, well, we better do that, right?
Okay.
AD and BE. Okay. And I suppose we could, okay, I need to figure out where my DocuCam is, and I guess go back to the DocuCam here. All right. So I'm going to draw a triangle with congruent altitudes. And I'm just going to make it sort of ridiculous looking so as not to prejudice myself as to so this altitude is supposed to be congruent to some other altitude. And the other altitudes are, so this is, say, AD.
Funny.
And
Sammy, but funny.
what was that? See, I didn't draw that right. I need to draw a more scalene triangle. And we'll try to draw it so that it's not equiangular or isosceles or whatever in an obvious way. So here's an altitude. And here's another altitude. So this is going to be A, D, and the other one is BE, huh? So okay. So given given that BE is congruent to AD, we'd like to show triangle ABC isosceles. And the baby step here is to let ABC have congruence, draw the figure for reference. Then by the blank of altitude, definition, right? Definition of altitude, the two angles, which two angles? BEC is one, and let's say ADB is the other. That's a little ambiguous, right, as to what they want. Consider the triangles ADC and BEC. They are both right triangles, yeah, with common angle ADC, what am I looking at? ADC and BEC. Oh, with common angle C, right. Yeah. LOC. Yeah, so that angle is congruent to itself, right? So I can say here that so they have one side and one angle congruent. Well, so yeah, so we know that angle EBC plus angle ECB is equal to 90 degrees because the sum of the interior angles is 180 and we already have 90, right? So by the same token, we know that angle CAD plus angle ECB is equal to 90, right? So that means that angle EBC is congruent to angle CAD. So EBC, CAD, those are congruent, right? So now we have angle, angle, side. So that means that angle or triangle EBC is congruent to triangle DAC. Yeah. By angle, angle, side. And so corresponding parts are congruent. So AC is congruent to BC. Corresponding parts of congruent triangles are congruent. Yeah. So when I go to fill in the answers, which are here, triangle CAD is congruent to triangle EBC. Because angles complementary is the word here. Thus, by the I think this was angle, angle, side, or side, angle, side, I think, or angle, side, angle will also work. Triangle ADC is congruent to triangle BEC. And since corresponding parts, congruent triangles are congruent, AC is congruent to BC as desired. All right. Yeah, I'm going to go figure out why why I'm getting these wrong. All right, so I'll go behind the curtain and edit these. But I need to go and see if so. Any other questions? And we'll take up with this tomorrow. Since it's obviously of some interest. Maybe I need to make more. See, there's a lot of ways of describing this angle, right? It could be ADB or BDA. I think I'm talking about the right one. Yeah. BDA or ADB. Or you could say ADC. Yeah, maybe it's ADC is what they want. Right. Yeah, yeah. See, it's true, but I mean, we want the corresponding one in that. Common angle C. Oh, I guess ACB maybe, is that? I mean, C would be enough to specify it, right? But, yeah. So now because angles complementary, I think that's supposed to be complementary. So I'll go and figure out why that isn't what it should be.
I think it's spelled wrong, Professor.
Oh, really? CMP, it's hard to tell because it's, oh, trary, complementary. Ah, very kind of you and keen to observe that. Yeah, okay, very good. All right, so shall we call it a wrap then? And was that Carla who pointed that out? Who was that?
Yeah, Carlin.
Okay, well done. Oh, Carlem. I have a Carlem Medina and a Carla Rivera.
All right,
Nice
have
one.
a great one, Professor.
Okay, have a pleasant afternoon, and I'll be in my office for a little longer. I need to go check to see if I'm missing somebody. Ciao for now.